right. Then it's 11:08, so I think we can continue with the next part. That Dave, I'll stop sharing my screen so you can take over.
Yes, thanks. Let's see here. Okay, yeah. So we have got our work cut out for us with the rest of this lesson in a sense, because we do have a bit of material to cover and not a ton of time to do it. But let's see how that all goes. And if we don't get through everything, that's not necessarily the end of the world, but it would, of course, be nice to cover what we can. So to continue, we are into the second file for this week's lesson, processing data with pandas. So if you open that up in your CSC notebooks instance, you should hopefully see something like this. Since we are working in a new data file, in this case, what we need to do is first import pandas. So you can just do Shift Enter. There's a question here in the chat. I'll just answer this very quickly. So yes, I think for the file path, if you're trying to load the file, for instance, in the exercise for this week for the file path, you need to have data / and then the file name. If you just put path or just data by itself, it'll complain that it's a directory, not a file. So it should be data / file name. Okay. So with our lesson, we basically need to get back to where we were before. And that is, we had read in this data file, Kumpula June 2016, with metadata.txt using the pandas read CSV function. And we need to do that again. So we will set here first. Maybe we can define our file path as FP, often used to define a file path. And we'll give the name of the file we're going to load in this case. I believe if I start typing in the file name and press tab, because the file is located inside this directory where we're working, you can type fp equals and then start typing in the file name and hit the tab key, or the one that, I don't know, at least on my Mac, looks like it's got an arrow pointing to the right with a vertical bar. Or you can type in this full string, but fp equals Kumpula, blah, blah, blah. And once you've defined the file path, then we can do data equals pd.read CSV. And now we can give fp as the name of the file, which we've just defined as the variable fp. And then again, we should skip the first 8 rows. So we'll skip rows equals 8. And this is more or less what we had done before. And just to make sure everything looks good, I'm just going to type in data here and press Shift Enter. And this looks like the same data file we were working with previously. So we have our headings here, your moda for the date, temp, max, and min for the temperature, the maximum temperature on that day, and the minimum. And then we have our index values here on the left side. So yeah, there's a note here that shows up a bit more nicely on the course page than it does here, but just indicating that what we're using is a relative file path. So because we're working in the directory where this file is stored, we can just say fp equals this. Alternatively, if we wanted to be able to have this notebook work in any location on this same machine, we could give an absolute file path, which is given, for instance, here, which is the file path relative to the root directory on the computer. So it's a complete file path. So if we copied this notebook to a different directory that didn't contain this Kumpula June 2016 data file, this would still work if we give the absolute file path. And this is something that is not a bad idea if you are working with notebooks that might be moving around to different directories. And there's also a note here about if you're going to do this, you could include this as a raw string. So like we have F strings with the F in front, raw strings have an R in front, and that helps with things like the interpretation of this file path. as it's shown here. It's not so much an issue in Linux or in Mac OS, for example, but in Windows, there's this tendency to use the slash that goes the other direction, which can be interpreted in a string as an escape character. So that's how you do things like this /n to do a new line. That's not interpreted as two separate characters, but as a new line character. So there's a note about that. Now, what we have done earlier is kind of look around at the data we have, but we haven't messed with modifying or really changing the data in any significant way. And we'll start with that here with some basic calculations. And our most basic calculation we can start with here is to add a new column called diff to our data frame. So we can do that by typing the data frame's name. And then we'll put in here in the square brackets diff, the name of the new column we want to have. And we can just set all of the values in that diff column to be equal to 0. So we're just essentially kind of initializing a new column with a value of 0 everywhere. And if we type then data, that should print out our data frame with this new column diff that's listed there. And sure enough, it's labeled as diff and all the values are 0 as we might expect. So that's good. Let's take a look here at the data type. So you remember that you can use the type function, or you can use .dtypes to check the data type. So let's do it the pandas way. So we can do diff .dtypes. That'll give us the data types of this single column since we're doing data diff. And you can see here that the type is float 64, and that is then a floating point number, as pandas has recognized nicely when we defined it, that a 0.0 value is a decimal value and has represented that as a decimal value in the data frame. So that's handy. Let's calculate now something instead of zeros, a meaningful value for the difference. So diff is meant to be used in this case to indicate the difference in temperature, and we can take the difference between the maximum and the minimum temperature to know how much the temperature changed during a given day. So for that, we can do, again, data diff. And now instead of setting it equal to 0, we can redefine the values there to be data max minus data min. It gets a little bit cumbersome with these brackets and quotation marks and things like that, but what you should have is data diff equals data max minus data min. And again, we can then just type data down here at the bottom or data.head to check the first 5 rows of the output of our modified data frame. So now when I run this, it should calculate the difference between the max and min and store that in a column called diff. And sure enough, what we see here is exactly that. Our diff column now contains non-zero values. And it looks like, if I just take a quick look here at max and min in this instance, it looks like it should be a difference of 25.8 degrees, and it is. And then here you can see we have a nan value. We've seen nan values, I think, already once earlier in the lesson that Håvard was giving, and this comes up that when you do math that involves some kind of nan minus something or something minus nan, you're going to always get nan back as your value. So if you try to subtract something from something it's not a number, or vice versa, you get not a number back as that part of the math. So that's handy. We can do math with the columns we have in our data frame in that way. Subtract values, add them, multiply, whatever you want to do. We can also do things where we have a little bit more involved calculations. So we could make another new column in our data frame. In this case, we can call it temp Celsius. So let's make it temp underscore Celsius. And this time what we'll do is we'll convert our temperatures from the average daily temperature in the temp column that's currently in Fahrenheit to the equivalent value in Celsius. And we can do that pretty easily. if we take here our, let's put some parentheses first because we're going to divide by something. We'll take our values that are in data temp. And we can take those minus 32. So part of our conversion factor in this case is to take whatever temperature in Fahrenheit minus 32. That's why this has to be in a pair of parentheses here, because you do that first. Then you can divide by 9/5. Or if you wanted to, you could multiply by 5/9, whatever you want. But that's what we do there to do our conversion. And once we've done that, we can then again type data.head to see our modified output and our converted temperatures. So we'll run that one. And here we have values of temp. I know that 68 degrees in Fahrenheit is about 20 degrees Celsius, and that's a good check. So pick, if you happen to know any temperatures in Fahrenheit and what they are in Celsius, it's always good to check and see if our function worked properly. And it looks like it did in this case. If it was 68 degrees exactly, we would get 20 degrees exactly for the temperature in Celsius. It's slightly bigger, and our value for our temperature is correspondingly slightly higher than 20 degrees, 20.2 repeating. All right. So I know we're maybe moving a little bit quickly, but now you have an opportunity to take a moment and check yourself for how things are going. And we'll do that by adding a temperature here, another column called temp Kelvin. And in this case, what we're going to do is calculate the temperature in kelvins from our temperature in Celsius that we already have. And we can note here that 0 kelvins is minus 273.15 Celsius, as we learned in lesson 4. So why don't you now take a moment, calculate your temperature in kelvins. And once you've finished with that, I'll pull up the participant list here. And there's already one green check mark, but once you've finished with this, you can please add a green check mark, and we'll continue once I see a decent number of the green check marks present. It looks like we have now 11 green check marks. I think there's 12, and I think that was Hovard's cutoff up to 14. Okay, very good. So yeah, we should continue, and let's do that. If you haven't had an opportunity to do this just yet, you can either plug your ears and close your eyes or whatever. But you can also find on the course page how the solution for this if you want to try it yourself at some point. In our case, all we want to do here is just add our temperature in kelvins by adding a new column to our data frame. So we start with data, then we can put here in quotation marks the name of the new column, which is temp_Kelvin. And we want that to be equal to an existing value we have, which is temp Celsius. So that's data temp_Celsius. Like that, plus 273.15. So that's our conversion factor. In this case, not really much to it, just adding 273.15 degrees to our existing Celsius temperature. And then if we look at data.head here, I can run this and see temp kelvins. And again, around 20 degrees is a good useful point because that's an easy number to look at. So 293 is, yes, 273.15 higher than 20 degrees Celsius. So looks good. All right, let's talk now a little bit about how to select values out of our data frame. So what we've been doing to this point has been taking an entire column, for example, and modifying those values. But what if we only want to do things with parts of our data frame? And it turns out that there's a few different ways you can do this in pandas. We can do index slicing, which is kind of how we've dealt with things like in Python lists previously, where we have a starting and stopping index value, and that allows us to pull out some range of numbers or values from our data frame. So for instance, with our data frame, we could make a selection. So selection is just a variable that we'll define, here being equal to our data frame. So data, and let's do 0:5. So this is like selecting with an index value in a Python list. We have a start index and end index. And now we're going to just take the first rows out of our data frame and store that as the variable called selection. And then I'll just type its name after that to have it displayed here in the screen in our Jupyter notebook. So yes, as you can see, we have here selected starting with index 0 and going up to, but not including index 5. So the first 5 rows, 0, 1, 2, 3, 4. And sure enough, that's what we see. Okay, so that's handy. And in cases, where I just want the first 5 rows, you can do this just like you would with a Python list. Or if you want the last row, you can do that just like you would with a Python list as well with index -1. We'll see that in just a moment. But there's more you can do with pandas. There's other ways you could select rows and columns in pandas. And this is really maybe taking steps in the direction of the more powerful way in which you can interact with your data in pandas. Let's imagine that we wanted to make a selection of the first rows of a data frame, but only a single column. So in this case, we'll take rows 0 through 5 of the column temp. And here our selection is now going to be data. And we're going to introduce a new thing here, data.loc, L-O-C, not L-A-C. Data.loc. So we're going to use this loc indexing. And we now can give some row indices. So 0 to 5, kind of like what we saw before. And then column indices. In this case, we're just going to give a single column. What's different here when we run this? So I'll just type again the name selection, press enter. There's a couple things. One, we now get 6 rows of data when we had 5 previously. That's because we're not selecting based on the row index, but rather on the label for that. As it turns out, when you do that with data.loc, it starts at a value and goes up to and includes the value in the range of the labels that you provide. So what we have in our, I'm just going to scroll up for just a second here to where we can see more of our data frame. What we have in our data frame is we have index values that correspond actually to the indices we would have in a Python list. That's a coincidence. It's not always going to be the case. In fact, frequently these labels will be something other than just a number 0, 1, 2, 3, whatever, but they might be a date or some other kind of label here. And when you do .loc, it actually looks at the label range that you provide. So that will go from 0 and include 5. And then of course, for the column range, we've only given a single column, which is temp. So if we scroll down to the example we're looking at here, what we see is 6 rows because we're going up to and including index 5 and a single column, in this case, temp. So just be aware of that difference because it is something slightly different than using an integer index. If we had dates, for instance, for the values that were labeled as the index in this data frame, we could still take data as we did up here, 0:5, and that would give us the first 5 rows, but these indices over here as the labels might be something like a date instead of a 0, 1, 2, 3, 4. So that's a difference. And notably with the .loc indexing, that's really a powerful thing because you can take slices of dates, for example, or ranges of dates very easily using .loc. Of course, we can also take multiple columns when we do this. So if we did the same thing we did before, we can have our selection here being equal to our data frame again. Data.loc, sorry. And we'll take 0:5 for the row index labels. And then in here, we can put in a Python list with the columns that we want. So in this case, we can have temp, and we can have temp underscore Celsius. So now we should have two columns, and we should have the first 6 rows based on the index labels. We type in selection down here again and run this cell. What you see is, as we did before, 6 rows, but now we have the 2 columns. So if you want to select more than a single column, you have to provide those in a Python list, because the expectation for loc is the first thing you give should be something about the row index. So you can see, for instance, here, start index, stop index. And then after that, the next thing should be a list of columns. If you give a single column, it can be just a string like this, but if it's a list of columns, it should be in the form of a Python list. So it basically is treated like a single variable or data object. I think in the interest of time, I will maybe just show you this check your understanding example for finding a temperature in the last 7 days of June using .loc indexing. So what we can see, if we looked at our data frame first, I'm just going to run this to see what our data frame contains at the moment. You can see it starts at index 0, goes up to index 29. And so if we want the last 7 days of June, so it'd be 1, 2, 3, 4, 5, 6, 7. So it should go from index 23 to index 29. And we can do that. So if we just said, for instance, data.loc, we give our rows 23 to 29. And then the column that we want in this case is temp underscore Celsius. So we've done 2 things here. Last 7 days of June, that's covered by our rows. Temperatures in Celsius is covered by temp Celsius, but it says here we should find the mean temperature in Celsius for the last 7 days of June. And in that case, we then need to add here the mean method, which will calculate from this slice of our data frame what the mean values are. I'll strip this off here for a second, just so you can see. So let's take that away for a second, just see if we get the right dates. So here we have the index labels 23 through 29. So that should be the last 7 days of June. We have here 7 days. And we have our temperatures. That all looks good, but those are the temperatures on each day. And if we add here .mean, we run that. And what it does is takes that slice of the data and calculates the mean temperature of 18.2539, blah, blah, blah. So that seems like a useful thing to be able to do, to select based on rows and columns. If we want to select a single row, we can, of course, also do that using .loc indexing. That's not a problem. All we do is just give a single row. And if we wanted, for instance, in our data frame to just have our single row, we could make a variable row here. It's just data.loc. So this will give us all the columns. Data.loc. And let's just say 4. So this should be the row index number 4. If I run this, what I see here is the name that comes back. That is the label for that index, row 4 in this case. And then all of the values that correspond in row 4 are listed here. So we can select a single row very easily using the .loc indexing. And what it actually returns is a pandas series as a single set of values where the label is the row and then the values themselves are in the pandas series. And if we wanted to see just a single value out of there, we could print, for instance, out for our row, what is the temp? And if I run that, then I get 51.4. And let's just take a look here. Temp 51.4 times 10 to the 1, or 5.14 times 10 to the 1 51.4 is the value. All right. The last thing that we'll show you about selecting values in this example is that if you want to take a single value out of a data frame, rather than using a combination of things in data.loc, it can be easier to use another method called dataframe.at. So here we'll select from the temperature column temp, the value that's on the first row, so at index 0. In that case, we can just go data.at, and the expectation now is that we're going to give a single value for a row and a single value for a column. So we say row 0, column temp. And if I run that, then I get back the single value here, 65.5. And if we scroll up just a little bit to our temp, we have 65.5 in row 0 of the data frame that we're working with. It's also possible to do this kind of selections by integer position. So this is kind of like the index slicing thing that we've seen earlier. So here, if we have examples of using this kind of iloc selection, we can select, for instance, the first two columns, temp and temp Celsius, and the rows based on their index in the example as it's shown here. So I don't even know if that second column is needed, or second colon. I don't think that's any different. I don't know why that's there. In this case, the iloc is going to treat it again like an integer index slice. So that's more like a Python list, starts at 0, goes up to, but doesn't include the row 5. And the same here, the first two columns, 0 and 1, are year moda and temp. Is that what's different? No. So it says we could select temp and temp Celsius based on their index, and then it shows an example here where we get year moda and temp. I think this ought to be 1 and 3, not 0 and, nope, that's temp and max. Okay. This doesn't seem to be working the way it's supposed to. Maybe there's a typo here in the lesson, so sorry about that. Anyway, the point is that you can do the selections this way as index values for multiple columns just as easily using the data.iloc. And so you can have a look at that at the page, on the course page if you want. We will mostly be using data.loc, so there's less concern maybe about doing that. But here, for instance, is the data.iloc -1, which allows you to get the last row of our data file. Okay, we still have a bit of stuff to cover here, and I want to have at least a moment to say something about the exercise. So let's keep moving ahead, and we'll see how far we can get with some of these other things. So we have now, to this point, handled doing some modifications of things like adding a whole column to our data. We have done some selections of rows and columns of our data. And our next step is to do some filtering. And what that means is to basically check and see certain conditions to help us with being able to interact with only certain parts of our data that meet a given condition. So for example, if we're interested in the warm temps, the warm temperatures we have earlier defined warm temps, I think, as being greater than 15 degrees. And we could take a look then, for instance, in our data file at the days when the temperature is greater than 15 degrees by typing data and then temp _ Celsius, because we're working with our Celsius temperatures. And then greater than 15 degrees. What this will output is a list of true and false values for each of the rows in our data file in terms of whether the temperature on that day was greater than or less than 15 degrees. So if it's greater than 15, it's true. Otherwise, it's false. And so you can see there's a couple trues, a bunch of falses, a bit of a mix, and then the later part of the month was all true in terms of being warmer than 15 degrees. That true and false and that kind of idea here of this true and false allows us to then take a selection of our data that meets a certain condition and use that to extract out only the values that we want to interact with. So I'm going to copy this data temp Celsius greater than 15 degrees, just because we're going to use it down here. And now let's take our data frame and make a selection of warm temps. So we'll call this warm underscore temps equals, and we'll use now data.loc. So this is our loc indexing to find in our data frame the values where the temperature for that day was greater than 15 degrees Celsius. So I've just pasted in here our condition. So data temp Celsius is greater than 15 degrees. This will give us all of the rows of the data frame where that condition is true. So that if we then look at warm underscore temps and print that out to the screen, we run this. Now you can see all of the different columns that we had before, but only those where the temp Celsius is greater than 15 degrees. And you can notice this right away because there's jumps in our index. So we have 0, 1, 2, and then it jumps to 13 and so on from that point. So that's kind of a handy thing to be able to use a subset or a selection to filter out values in that way. And we're using, again, our data.loc to do the selection and to use then our condition that the temperature in Celsius should be greater than 15 degrees for that day. It's, of course, also possible to have multiple conditions. We've seen examples of this when we looked at conditional statements. So if I copy this, I'll take this example that we have just to save typing in, and you can maybe do the same. We'll scroll down here a little bit and now make another selection. And in this case, what we're going to select is the days in which the temperature is greater than 15 degrees, and we're in the second half of the month of June. So that means that the date should be greater than or equal to the 15th of June in this example. So I'm just going to paste what we had before. That was at our only one part of the thing, and that is the temperature is greater than 15 degrees part. I'm going to put this in parentheses because we're going to have two conditions, and it's often easier to see that you have two conditions when you have them wrapped in parentheses. Then I'm going to add here a bitwise and operator. I'll tell you what that means in just a second. And then we'll have another set of parentheses here. We're going to have a second condition. And that is, in this case, that our data in the column year, mode, so year, month, and date, or day, like that, must be greater than or equal to, and then here I give a number value, 2016 for the year, 06 for the month of June, and then 15 for the day. What this means is we're going to first create a list of true or false values here for data when the temp Celsius is greater than 15 degrees. This will create a second list of true or false values for whether or not we're in the second half of the month of June. The bitwise operator and here will give us as its output the values or the rows where both of these conditions are true. So it has to be greater than 15 degrees and it has to be in the second half of June. So what that returns in the end is from the two lists of true or false, a single true or false that then can be used to select only the values that meet both of these conditions. That might be a little confusing, but let's just run this, and I think this will make more sense here when we output our warm temps. So what we saw before was temperatures of greater than 15 degrees. Let's check and make sure that's still the case. Yep, looks like it is. And now with the dates, here's June 15th and going up from June 15th. And if we scroll back to our earlier list, we had some cases where we were looking in the beginning of June at temperatures above 15 degrees. Those are all now missing. And you can see it, of course, that our index starts at 14 instead of 0, as it did previously as well. So that's our way of selecting a subset of our data with more than one condition. So the things to keep in mind here are just to put these in parentheses, these conditions when you have multiple conditions, and to use this bitwise AND operator that will allow us to select the conditions when both of these things are true. Now, when you're doing this, occasionally, it can be useful to keep the index that you had originally. Might help you in knowing that you've lost some of your data to keep the original index around, but sometimes you also want to drop out your index values. For instance, if you're filtering out a bunch of data you don't want to ever use, you may want to reset your index in order to then be able to select by index by the index labels or the row labels, for example. And we can reset the index here for our case by saying our warm underscore temps equals warm underscore temps dot reset underscore index. Underscore index. And here we're going to say drop equals true as well, capital T and true. And then we'll take a look at what we have in warm temps. Okay, before we do this, so reset index will reset the index numbering, so it starts at 0 again, as it did previously. Drop equals true will not, will basically prevent us from adding in a column to our data frame that contains the old index values. So if you don't include this, then you'll get another column called index in your data frame that has the old values for the index. And that can be handy, but in this case, we're just going to go ahead and drop it. And what you can see is our index now that's given here starts at 0 and goes up to 12 for the 13 values that we have in our selection. For this next check your understanding, I think I will again refer you to the course page that you can take a look at how to select things on the basis of conditional statements. And there's an example you can find on the course page of how to do that. It's not so different than what we saw before, but just a different approach for calculating the mean temperature in the last 7 days of June. Let me see what we have left here. We have to deal with missing data. We have to deal with type conversions and unique values and sorting and writing to a file. Oh boy, we have a few things left here. Some of these you need for the exercise. So I'm going to maybe go through this stuff, and I think what I can maybe do is I will finish the lesson and record it. And if you're able to stay here, that's great. If you're not able to stay, then no worries. I'll put the lesson video up that will have the complete rest of this lesson. Because you need it in the exercise, I don't want to really not present it and then carry on from that next week. We really need to use it this week in the exercise. So I think I will go through the whole exercise, and I do understand we're going to go over time a bit. So the other material that you might not catch currently, you can look at the lesson video to see. And apologies about going a bit long today. I guess maybe we had a bit too much introductory stuff. But yeah, I'm going to skip the rest of the kind of check your understanding things. You could do those on your own if you're interested to test that out when you have the time. So let's move to dealing with missing data. This is a very common thing that you load in a data file, and the data file has, for instance, observations from every day or every hour. And of course, they're not always recorded, so there could be missing values that show up in the form of an NaN, as we have seen in our data frame that we're dealing with at the moment. So if I just take a look here at typing data and running this, I can see, for example, in diff and max, we've got NaN values. And in several of the other rows, here's one in the min column. And of course, there are a number. And if we want to clean up our data set, sometimes you want to say, okay, if I'm missing a temperature value or something like that, just drop that row entirely. Let's do that here by looking at the rows where the min column has an NaN. We can drop first based on that. So we'll take our warm temps rather than our whole data frame, warm temps. And let's say warm temps clean equals warm temps. Actually, you know what, before we do that, let's just take a look at what we have in warm temps. Do we have NaNs? Yes, we have NaN here and NaN here. They're both in the min column. So if we drop those out, those rows that contain an NaN, there should be nothing left that has NaN in our data frame. So warm temps clean equals warm temps underscore temps dot drop NA. So drop NA is the function that will allow us to drop missing values. And in this case, we're going to say subset equals, and we should give this in a form of a list, min. So there's a single value in here, subset equals min, like that. But of course, if you had multiple columns, you could give your subset as a full Python list. We're giving a single one in this instance, but I think it does expect the subset to be a list. So this will drop any row that contains an NA value in the min column. This subset equals min thing is handy because sometimes you have, for instance, NA values in other columns and you don't want to drop those rows. So here you can say, okay, if you only want to drop rows where a certain column has min or has a NA value, you can do that. And if we then type out warm temps clean here and run this, what you can see now is we've lost a couple values. So row 9 and row 11 are gone because they had NA values and nothing else in our data frame at this point has missing values. So you can call this our clean data. What we did in this case is we did this drop NA and assigned it to a new variable called warm temps clean. There's a note here that says if you want, you can also do this in place. So if you don't want to create a new data frame, you could say, for instance, warm temps.drop NA subset min in place equals true, and that will then drop that out of the warm temps data frame. So that's a handy thing to know about because you don't always want to have to make a new data frame, especially if you're just cleaning out your data. You may just want to have like data dot drop NA and then give the subset of columns you want, and in place equals true. Another thing to know about with these missing values is that there are some cases where you want to replace an NA value with some other numerical value, for instance. So sometimes, for example, with GIS software, it might not understand what NaN means, but if you give a value of -9999, you can tell it that that's the missing value as indicated in the data file. So we could take, for instance, warm underscore temps, which is not our clean one, but our original, and do dot fill NA. And then in here, give -9999. And what that will do is replace the NaN with -9999. And so here you can see now that replacement that has taken place in our original warm temps that still had the NA values present. This is good to know about, and it's okay to use in certain circumstances, but of course, it's also dangerous. So if we were to try and now calculate, for instance, what the average min temperature is in June or the second half of June, we'd have these -9999 values in there that are going to very heavily influence the average temperatures. So you have to be a bit careful with how you use this, but for some GIS software, it will recognize these values and it wouldn't recognize NaN. So that's why we introduced that here. All right, let's do a couple examples now of doing some type conversions. This is rather common thing to do as well, just like you would have to convert your floating point numbers to an integer or integers to floating point numbers with normal data types. You often will do the same thing with with pandas. So here you just need to run this cell. This will tell us what our original data in the temp column looked like. And since we're doing .head, it's just the first 5 values here. This is the original values. If we imagine we wanted to round these or change them to integer values, we can do that in pandas, of course. And the way to do it would be to do something like data and then temp. And now what we can do is temp.asType. So this is how we do our type conversion. As type int. We'll convert our value from a floating point number to an integer, and then we can just do .head on top of that. So we only get the first 5 rows. So we run that, we get integers back. You can see here now the data type is int64 instead of float64. But you might be looking at row 2 going 65.8 has now been truncated to simply 65. This is something to watch out for with these type conversions, is if you take floating point numbers and convert them to integers just like this, it just truncates. It does not round the values. So it says, oh, see you later decimals, and that's it. It doesn't worry about what the decimal values were. If we want to round them, then there is a way, of course, to do that, and you should do the rounding first and then the type conversion. In this case, doing data temp dot round, and here we're going to round it to 0 decimal places, so that'll round to whole values, and then dot as type int, so that'll convert. Even though it's been rounded to 0 decimal places, we still would be a floating point number at this point, and then we do the dot as type int to convert it to an integer whole number value, and then dot head just to see only those first 5 rows. And now you can see that 65.5, 65.8 have been rounded up to 66 as you would expect. 68.4 is just rounded down to 68. So that's how that works with the type conversions. Going from floating point to integer values, this is something to be careful with the rounding. You really want to make sure you don't just truncate things, because obviously that can become problematic. If we were, rich Wall Street kind of financial people, you could imagine there would be a lot of dismay if you just truncated everyone's bank account values at the decimal places. There would be sort of, I don't know, there's probably some kind of movie where, I guess actually I think the movie Office Space, if you've seen that, I think one of the ideas with that is sort of truncation of parts of a cent or something like that into bank account to get rich and whatever. So, okay, you can use this for nasty things if you want, this truncation, but just be aware that it could cause problems. I'm going a little off the rails here. Unique values are also something you will occasionally want to do. This basically allows you to identify, for instance, in a data frame, how many unique or different values you have in a given column, for example. So if we looked in our temp column, we could have data here, temp, and we've already got the unique variable name in there, which is handy. Not temp, but temp. So data temp dot unique. And this will return a list of all of the values that are unique and listed only once, instead of if they're repeated multiple times, they would only be here coming back one time. So if we then type unique and run this cell, we get a list of values that comes back here. These are all the temperatures that are uniquely or only one time listed in the, they could be listed multiple times in temp, but here is the unique list of the different temperatures. For temperature values themselves, maybe unique is not so interesting, but if you had things like, responses to some kind of question, then maybe you would like yes, no, maybe, whatever. You might like to see what all the different kinds of responses you got. You could use unique for that, for example. This, if you had a really long list, will often get displayed in kind of a shortened format. They'll put in an ellipsis in the Jupyter notebook so you don't see all the values. And it's just noted here, if you want to see all the unique values, you can always type list and then unique, and that will show you every single one of the values in the form of a Python list like this that would not be truncated, even if it's really, really long. This will still show all the values. So sometimes you want to check all the individual values like that. And then here is the question of how many days with a unique mean temperature did we have in June 2016? So the opposite would be to say, like, how many days were there in June that had the same temperature? We could figure out the same thing this way, but what we can do with our unique temps here is take the length of unique to tell us how many unique temperatures there were during the month of June. And then we can print that out using the F string that's listed here. And now we see there were 28 days with unique mean temperature in June 2016. So that is use of the unique function. We'll show you just two quick examples of sorting data and then how to write to a data file. And again, I do understand if some of you need to leave at this point, but this will be part of the lesson video that goes up on the course page. So I think it's better to finish than to skip this at this point. And now let's sort some data. This is as you can imagine, something you would also want to do. Sorting temperatures, maybe not. Sorting dates, that could be something you would want to do. And possibly you would want to sort temperatures. And so in our example, what we'll do here is we will sort the temperatures. We can do that by doing data.sort values, sort underscore values. And then here we say by equals temp. So this will sort our temperature values in ascending order. Actually, we'll sort all of our values in our data frame in ascending order by the temperature. This is kind of like if you were in Excel to go to the temp column and then sort that column, you would see all of the rows get organized or reorganized accordingly. So now you'll see our indices are all mixed up. And that's because we start with the coldest temperature and go up from there to the warmest temperature in the month of June of 2016. Okay, so that's how you do things ascending. Easy. Let's copy this one. We could just as easily or nearly just as easily make our sorting be descending or in the opposite order by adding in a parameter here in our sort values to say ascending equals false. So by default, it will sort in ascending order. If you want things in reverse order, you can do ascending equals false. Run that, and sure enough, what we see, temp 69.6, and then going down from there to the temperatures earlier in the month where it was only 49.4 Fahrenheit. So we can do lots of different kinds of things here to process and interact with our data in pandas. That's just two quick examples of how to do the sorting. The last topic we have for the lesson today is about writing data to a file. And you can imagine that this is also a very common practice. You have gone through and read in some data file from a database, for instance, of climate data. It's had lots of missing values that you've stripped away. You've calculated new values, converted temperatures from Fahrenheit to Celsius, and done all of this stuff. And you want all of that work to not just disappear when you close your Jupyter notebook, but to be saved in the form of a file. And in our case, we will write this out to a CSV file because the comma-separated values format of a data file is one of the most common and easiest to interact with. So that makes a logical choice for us to use in our examples here. To do that, we first can define an output file path. So let's make a variable here called output underscore FP. And our output FP in this case equals, let's call it cumpula, how about temps June 2016 .csv. So those are the things that we have to provide here in the name of the file. And now we need to provide a statement for how to write that out. And that is to say that we're going to take our data frame data and .to_CSV. So that will write this to a CSV file. And then we should give our file path output_FP. So that's the name of the file that's going to be written. And in addition, we can give this parameter called sep, which indicates that the value should be separated by a comma in the data file that we write. You might go, of course, it's a comma separated value file. Why do you need to specify a comma? And that is because you may want to use another character like a semicolon or something else, depending on the data that you're dealing with. For instance, here in Europe, in a lot of places where a comma is used as a decimal place, it makes a rather poor choice if you're writing out decimal values to have a comma as a separator. So instead, you might want to use semicolon or something else. But in this case, we run this. And if you run it, what you'll see most likely is that there will be a new file that appears. And you can double click on that if you would like. And you'll get a preview of the CSV file here in your Jupyter notebook, where you can take a look and see, that all of the values that you're expecting to see are indeed here in this notebook. And in the file that you've saved in the notebooks. So that's nice, but hold on a second. If we look at this, one thing that's not so nice is there's a lot of decimal places here for a number of these values. And maybe we don't want to have quite so much precision written out to our data file. This is really kind of artificial. We don't have any sort of significance to having 16 digits of precision, for example. So let's try this writing exercise one more time, but let's do it with some additional steps to clean the output so it looks a little bit nicer. So let's set an output file path again, output_FP2. And in this case, we'll call this one Kumpula again. So Kumpula temps_June. Now, actually, let's do temps above 15, June 2016.csv. So set our file path. And now, just like we did before, instead of data this time, we're going to have warm temps.to_CSV because we only want these above 15 degrees temperatures. We have our output FP2, like we did before. We have our sep, like we did before. Sep equals, in this case, comma. And we can maybe get rid of this index column because we had that here. That's really not useful to us so much in our output file. It's just numbers and it doesn't mean anything. So we'll just say index equals false. So that will suppress output of the index. And then we'll set our float format equal to, and in this case, it's going to be %.1f. Little bit weird notation here, but our floating point format is essentially saying whatever the value is, so that's the %, kind of a filler there, should be given 0.1, which means it should be decimal with a single number in terms of the precision, and f as a floating point number instead of writing like scientific notation or something like that. You run this one and you get an error because I've misspelled output FP2 somewhere, output_FP2. Run that, and now you get another data file. This one says it was created seconds ago, so that must be the new one. Double click on that. And here we have now from the 15th of June on our warm temperatures. You can see where there's missing values. It's just empty in our output file. And our temperatures, most importantly, have been rounded to a single decimal place. So the output looks much nicer and cleaner in this form. I think we made it. So that was our pandas lesson. Again, I know we're over time a little bit, but I do want to just walk you through the exercise quickly. Are there any questions at this point? I still see a decent number of people here online. Thanks for joining in. If there's not questions, I should go find the right exercise, which is not exercise 2, but exercise 5, which is our exercise for today. So just a quick introduction to the exercise for today. As you can imagine, we're going to be using pandas, working with a data file to interact with some climate data. And there's a bit of a description here on the course or on the exercise page that explains the format of the data file. You can see it looks a little bit busier. So the data file was taken from a climate data database, and it's got a lot of columns that we do and do not need. We've got things in here like missing values filled in with different numbers of asterisks. So that's fun to deal with. And we have our observations of the temperature here in a different format. So it's year, mo, da is what we had before. But now we have her moon, so for the hour and minute of the observation as well. And you can see here that the data file looks a little bit more intimidating than we had previously. We also have observations from Helsinki Kumpula as well as Rovaniemi. And because of that, then we have to think that this first column, USAF, is the station ID number. We'll have observations from different locations. So that's the data file we're working with. The first problem is more or less just to kind of load and interact with the data file. So you will read it in using pandas. You can use the read CSV function to read in the data file, and you're told here that if you supply in your read CSV function NA values equals this, it will convert anything that's a single star, double star, triple star, etc., to a NaN value. So that's how it will convert the missing data values to NA in pandas. Once you've read it in, you can print out how many rows there are, how many columns, what data types you have, and then figure out what the mean Fahrenheit temperature is, what the standard deviation of the maximum temperature is, and how many unique stations exist in the data file. And you're told basically how to do that. That's it for the first problem, just basically loading in and playing with the data. Problem number 2, we're going to do a little bit of data manipulation and selection. Again, we start out by loading in the data file. We use the same file that we used in the first exercise, so you can take your steps for loading in the data file from the previous problem and just copy paste that here. The first step is going to be select only a subset of columns that we need. So we don't need all of the columns in the data file, but we'll just pull out the ones that we want to work with. So the station ID, date, temperature, max temp, and min temp. And then we can also remove all the rows that have missing data from the temp column using the drop NA functions. That'll clean up our data file a little bit as well. The next step will be to convert the temperature in Fahrenheit to temperatures in Celsius. We've seen this equation before, although I don't know why it's got these little wiggly lines in here. Those shouldn't be there. Maybe that's a GitHub thing and not something that's really going to show up in the notebook itself. But that's the equation for converting as we have previously seen. So we'll do the temperature conversion and then round the temperature values in Celsius to have 0 decimal places, and then also convert them to integers so we can practice using things like the as type method. The next step then is to separate our observations for Rovaniemi and for Kumpula, and we'll do that by selecting on the basis of which station ID is there, and we'll make then 2 separate data frames from those selections. And finally, you can then save those values that you have selected in your new data frames to output files and write those using the 2CSV method. Problem number 3 is doing a bit of data analysis. So again, we've got to reread in our data files. You just will have created these 2 CSV files and you'll read those in to start problem 3. Then we're going to calculate some things like the median Celsius temperature that's observed in Kumpula and Rovaniemi. And then those will be printed out to the screen. Then what we'll take a look at is a subset of the data. So the median temperatures before were for the entire summer, so May through August, but we can select, for instance, just the month of May and just the month of June and calculate median temperatures or mean temperatures, I think in this case, for those months. So you do that for both May and June for Kumpula and Rovaniemi. And again, that'll be printed out to the screen to see that everything is working properly. And now you can print out a few useful values here to make it easier to compare our temperatures. So you're asked now to print the mean, max, and min Celsius temperatures for both locations using some of the existing data frames you will have created. And then that's basically it for the end of that problem. Problem 4 is an optional problem. So if you're interested, you can do this for your own enjoyment. But essentially what we're doing here is something that we'll learn about in the following week's lesson, and that is aggregation of our data and taking things like what we have right now, which are, as you can see here, this is our year, month, day, hour, min temperature observations. And you can see here is something at midnight, 20 past midnight, 50 past or 10 till 1 a.m. Here's an observation at 1 a.m., 1:20. So we have multiple observations per hour in the data that we have. And what we want to do is combine that down to just a single temperature value as an average for that day. And that's what problem 4 is all about, is taking things from hourly observations or more than hourly observations and compressing that down to daily observations for the data that we have in the exercise. All right, sorry about going a bit long. I hope that that you guys aren't completely depleted here. Are there any questions at this point? Not seeing anything in chat. I am very nearly done with the feedback summary for the course feedback, the midterm feedback. So I'll post that on the course page here sometime today and send you all a link maybe in Slack so that you can see what the midterm feedback looked like and check and see that what people have said more or less fits your experiences. Otherwise, I'll encourage you once again to sign up if you want to attend the exercise sessions in person. And if you have any questions in the meantime about the course material for this week's lesson or the exercise for this week, you're most welcome to come to the exercise sessions online or in person, or ask us a question on Slack. I think that's it for today. And next week, we'll continue on with our pandas adventure and getting into a little bit more advanced data processing topics. There's a question here in chat. Were we told how to import stuff from a folder? I don't think we had an example about loading something from a subdirectory, but we can maybe just do a quick example. Let's see here. I'm going to just very quickly make a new terminal window because this is how I know how to do things. And if I had here in the notebooks L5 directory where we have been working for this week's exercise, I could make a directory called data. And I'll copy the data file we've been working with, the Kumpula June 2016 with metadata file, to the data directory. So just so you can see, we now have data, and inside there we have our data file. If I was going back to the very beginning of the lesson, I think I can close this now, to when we first loaded the data file. So scroll all the way back up here. We had set the file path equals Kumpula June, whatever. All you have to do is just add in the data / Kumpula June, and that should now work. It'll look in the data subdirectory. And if I run that, yeah, it runs without giving an error message. So it is finding here in the data subdirectory this file called Kumpula June 2016. that's the way to load something from a subdirectory. Of course, we could give the full file path if we wanted to. So, I mean, if I look at the current working directory that we're in here, this gives the full path to where we are. I could copy paste all of that stuff in here for my file path. And now that's going to be a file path that will work. If I move the notebook anywhere, this is the full path to finding this data file. So I don't need to rely on a relative path, which is a path that's finding the file relative to where we are right now. But this will do the same thing. And this is more flexible in the sense that if I move the notebook to a subdirectory, it doesn't break anything. So you can think about whether you want to use the absolute path or just the relative path. But either way, all you have to do is just add the directory name in the front of the file path, and that should cover it. So yeah, good question. Anything else? Okay, I think that's it for today. So thanks for hanging around for those of you who stuck it out to the end here. And we will see you in the exercise sessions. And otherwise, catch you next week for our continuation with pandas. So, okay.